Hello everyone. Our project topic is real-time collision-free navigation of multiple autonomous vehicles. In today's self-driving industry, decentralized collision avoidance is a fundamental problem. And to tackle this, we have taken up this topic. So now let's look into our problem statement. First and foremost is that we are working with autonomous vehicles. Hence, we need to consider a non-holonomic constraint for this problem. On the right, we see a figure of a bicycle model. Next, is the vehicle's ability to avoid and plan the path ahead when a moving obstacle is encountered in its field of view. This moving obstacle could be a large truck, a person, or a self-driving car itself. So here we use velocity obstacle, optimal reciprocal collision avoidance, and acceleration velocity obstacle formulations to solve this issue. Third is to design a controller. Here we have used a model predictive controller, which enables us to incorporate various costs for the local path planning of the vehicle. Fourth being, we need to consider other moving vehicles and if they would react in the same way. So here we assume that either we have a non-reacting vehicle or a vehicle that reacts in the same way as we would. And finally, the most important factor here is that there's no communication between these vehicles, and hence this is a decentralized system. The main application is in the field of self-driving vehicles. Next, we could also extend this formulation for a truck or a trailer type vehicle. Here on the right, we see a kinematic model for a truck or a trailer type vehicle. Next, we could also use it for a crowd simulation. And finally, we could also use it for doing traffic engineering problems. So to build an understanding and background for the project, we focused on mainly 4 domains. One is to have a general review of the entire topic regarding velocity obstacle collision avoidance. Second is we tried to understand how to develop a kinematic model for unicycle, bicycle models. Third, the velocity obstacle and reciprocal velocity obstacle algorithms, which are there, mainly being the acceleration velocity obstacle, then normal generalized velocity obstacles. And finally, for the control techniques, we use model predictive control, and the paper is given below. So now let's look into the proposed method. The solution to the problem consists of majorly 2 parts. One is to design a global planner and then to design a local planner. The images shown are a good explanation of what is the role of each. So here the gray are the nodes, and to connect from the goal to the start, we use a global planner that finds the shortest path across these nodes. Now to plan a path between these nodes, we use a local planner, and it could be a model predictive control in our case. So now let's look into the depth of each planner. So now let's look into the global planner. We can approach the global path planning problem in 2 ways. One is to randomly sample n nodes, or we could actually smartly sample it at the junctions. So here on the right, we see that we can place these nodes on either T intersections or wherever there's a turn. How is this better? Because now the number of nodes are less, so it's computationally cheap to find the shortest path. But there is an assumption here that we would require to know the map from the start, which is usually the case when we have the GPS data for autonomous vehicles. Now, once we have the weighted graph, we can use the A-star or Dijkstra's algorithm to find the shortest path. For our project, we'll be using the A-star search. Now, let's look into the depth of the local planner, and for that, I call upon Fennel.
Now let's dive into the local planner. For our case, we utilize a model predictive control. Model predictive control is an optimal control strategy which consists of a state model, objective function, and an optimizer. The state model is used to predict the behavior of the system over the planning horizon. Here the state model is equivalent to the motion model of the vehicle, that is the kinematic bicycle model. The optimizer optimizes the future control inputs and minimizes the objective function over the entire planning horizon. Here we use RMS-prop as the optimizer because it is the state-of-art optimizer which approximates the curvature of the loss function without actually calculating the Hessian, which makes it faster. And we will also include the use of AutoGrad package that will help us efficiently calculate the gradient of the loss function. Now, the objective function consists of the goal reach cost. This goal reach cost is basically the Euclidean distance between the current pose of the robot and the desired pose of the robot. The smoothness cost is basically the difference between the current control inputs and the previous control inputs. We can also add workspace constraint to the objective function. Workspace constraint basically takes care of the map, the area of the map, and the static obstacle inside the map. Static obstacle cost is the distance between the inverse of the distance between the current position of the vehicle and the obstacle. And we can also start including the static obstacle cost only when the vehicle is inside a certain region around the obstacle. And the dynamic obstacle cost. This dynamic obstacle cost is modeled using ORCA or AVO formulations, which is the main part of the project and which is subjected to the constraint on control inputs. To carry out the experiment for this project, we considered a map having polygonal obstacles. The implementation of this toy problem is done using Python. Here, to simplify the computations for the configuration space, the autonomous vehicles are assumed to be a circle of certain radii. However, the vehicle will still follow the kinematic bicycle constraint. All the polygonal static obstacles are approximated using Lame's curve in the configuration space. The dynamic obstacles are assumed to be circular in the configuration space. Also, these autonomous vehicles have limited field of view and can only see obstacles in their field of view. To compare the performances of the algorithms implemented, we have decided on 4 performance matrices, that is time to complete the task, clearance to the obstacle, smoothness of the traverse path, and length of the traverse path. To carry out the experiments, we decided upon 2 kinds of experiment, that is for single vehicle navigation. In that, we further divided on 2 cases, that is in case when it only has static obstacles in the environment, which will help us evaluate the performance of the MPC controller, and in the second case when it has non-reactive dynamic obstacles, which will help us understand the behavior of a single robot around a dynamic obstacle. And the other case in which we use simultaneous multiple vehicle navigation, which is the main crux of the project and which will be discussed further. So now let's look into the preliminary results. To begin with the project, we put our focus on the local planner. And to initially model the system, we modeled the obstacles as circular obstacles, and we begin with taking the unicycle models that we will change to bicycle models in the future. And we solved the problem using the model predictive control. For this problem, we carried out 2 simulations. One was a simple goal-reach problem and the another was goal-reach problem with obstacles. The first simulation was a simple goal-reach problem where there were no obstacles. Here, we can see the state of the robot are 3 states, X, Y, and the psi angle. And after implementing model predictive control, here we see that the robot state going to 0, and here the another robot state also converging to 0. And here we can see the control inputs are within the bound, that is within lower and higher limits. The second simulation was a goal-reach problem along with the obstacles in the environment. Here we can see in the plot that is generated after the simulation that the robot moves from the start to the goal without colliding with the obstacles. It is ensured, as it is seen in the plot on the right, that the distance between any of the obstacles and the vehicle is never 0. That means it is not collided. This is the task distribution and schedule and timeline for our project. Learning objectives. Designing the kinematic model for non-holonomic robot constraints. Formulation of velocity and acceleration velocity obstacles. Designing and implementing a model predictive control. Handle decentralized multi-robot systems. Coding skills in Python. And the most important, teamwork and time management. The project deliverables are toy problem implementation of velocity obstacles, optimal reciprocal collision avoidance, acceleration and velocity obstacles. Utilizing an MPC framework for a car-like autonomous vehicle navigating amongst polygonal static and dynamic obstacles and comparing them on performance comparison matrices, comparison of ORCA and AVO with VO method. Stretch goal is extending the toy problem implementation for non-homogeneous cases, that is interaction between different kind of vehicles such as car and a trailer, a holonomic mobile robot and a differential drive robot, etc.
I hope you guys liked the presentation. That's all for today, and we are really excited to work forward in this project. So it's me, Samarth, and
Fenil.
signing off. Thank you.